在群里说一下好不好 ？OK OK。首先啊，大家先麻烦大家打开一下这个 notebook，就我刚发这个 notebook，一定要把这个先做完，先把这个 git clone 给做完。哦，可以可以。So you should be able to see the notebook in the WeChat group. There's no link.
Excuse me. Send the link again, maybe in the Zoom channel.
Right now.
Honey.
Learn some kind of new skills, which is like the skills we never actually like touched before. So it's basically about 3 different parts. The first part is called stochastic gradient descent. The second part is called encoding, and the next part is called, a wild rabbit. So I would say the hardest part is actually this part, the rabbit part. This is like a whole new library. This is actually the whole new library that actually is very different from the previous library, like sklearn library or pandas library we had before. This is more like a Linux library we're going to use, but this is a really powerful library because it uses online learning, which I'll explain later, which actually trains the model faster and also use as less memory as before. So this is a very useful library, but also the hardest part. So the outline looks like this. I'll go ahead actually introduce the stochastic gradient descent and online learning. Then a lot of other lectures will actually keep going from the second part until the third part. And last part is actually the demo. I think the demo goes back to the first part, the stochastic gradient descent. And the lecture will show you how we are going to use like a sklearn library from stochastic gradient descent to actually do some regression or classification. Okay, so first of all, like I mentioned before, because we're using most of the data set is actually from the ML course AI website. So you are gonna clone all the repositories from the GitHub so that you can actually use the data. So once you finish that, you click the left hand side, you can see the this kind of like file folder here, and there's everything's over there, and most important is like the data we're going to use is actually right here. Okay, so first part, stochastic gradient descent. So this is actually the most commonly used like gradient descent skills nowadays, because in the traditional way, like the traditional or conventional gradient descent has some kind of drawbacks. So first of all, I'm gonna refresh your memories about what gradient descent is. Then I'm gonna actually introduce what a stochastic gradient descent is. So if we just go back to the first several chapters, we actually talked about it before. Gradient descent is actually we try to find a way to minimize the loss function, and we try to find the slope. Then we actually goes along with the slope, and we find the learning rate that are actually going to decrease until we reach the local minimum over there. So for example, suppose we're using the weight and height data set. So I'm going to run this first, and we only have 2 kind of like variables, height and weight. Okay, so if you just plot weight as x, horizontal axis, and height on the vertical axis, you can see, oh, this is more like a linear regression. So that's what we're gonna do. We want to do a linear regression, but what like the central or the core task is actually try to find, for example, is try to find this regression, y equal to w0 plus w1 x1. What is w0? What is w1? The coefficient. right here, the intercept and the coefficient of the weight. So x here will be the weight, and y would be the height. So that is, we want to actually figure out what kind of correlation between the weight and height. Okay, so one way to do that is we can just do a gradient descent. So the first step to that is actually we need to find like loss function. So for linear regression, naturally we'll just come up with the ordinary least square. That is, we do the summation between the real y and the predicted y here, and we use a square to actually make sure we don't cancel the residuals with each other. So this is the square distance. So gradient descent is that we update two coefficients here, the intercept and coefficient simultaneously using the two forms here. So this part, the first derivative of the loss function with respect to the corresponding coefficient is called gradient. Okay, so this part is called gradient. And this part is called learning rate. It's called learning rate. Basically, you try to reach the real kind of like W0, W1, one step further. So how big the step is, it depends on the learning rate, and which direction it goes, it depends on this. So this is more like, so those two together can be the captain with the ship. So one captain tells you which direction you should go. That's this part. Another captain tells you how much you should move. Okay, so that's a gradient descent here. So if we actually plug this back to using this loss function and replace that part, just do the first order derivative of this with respect to W0, W1. This is a gradient descent like a function we're going to have. That's the updated, like how we update W0 and W1. Okay, so if that's the case, we have a really, really big problem. I mean, if the data set is small, that's okay. For example, if L here, see, so the most important part is we try to sum up. See, this is the residual y minus this part is predicted y. So we try to sum up all the residuals here. Okay, all the residuals here, but it has to be started from I equal to 1 to to L over there. Okay, so that means if L equal to 2, that's fine. We can just do 2. We can just do the 2 summation, like 1 plus 2. If I equal to 3, that's fine. But what if L equal to 3? Sorry. But what if L equal to 1,000? 10,000, 100,000. That means you are gonna do 100,000 summations here. So that every single time when you try to update W0, you have to sum up 1,000 observations, 1,000 residuals over there. So this is a huge, huge amount of calculation. So that's why the traditional gradient descent doesn't really work in this way. I mean, it will work, but it's probably going to take hours or even days to actually figure out W0, W1. Okay, so that's a drawback. So this is called, sometimes we call this dimensionality. So I'm going to write this dimensionality, cursor dimensionality. Curse of dimensionality. That is, you have too many dimensions, you have too many observations. Every time when I actually try to update W0, I have to, for example, the dimension is actually, for example, it's 4,000. You have to repeat 4,000 times to get a 1W. Then when you update again, you have to repeat another 4,000 times. So it's going to cost a huge amount of time. There's too much like, calculations over there. So this would be one kind of problem we have for the traditional gradient descent. So what we do here is, so this is the traditional part. So this is the traditional gradient descent. So what we do here is we try to manipulate this part. We try to change that part. Instead of sum up from 1 to L, why not just randomly select one observation? Why not just ignore the sum? Just ignore the summation, just do 1. We don't sum up, from 1 to L. We just, just extract one of the observations and want to do that. So if we do that, so basically just like what is that here, we throw away the summation and we update the weights only over single, training samples. So it depends. Sometimes we actually use a little batch. We use like maybe 3, 4 different observations, and we do summation over the 3 or 4 different observations over there. So we try to reduce the amount of summation, or we just extract one. We just do one. We don't do the summation. Okay, so that's either a single sample or a smaller number of the samples here. So this is this is the case of the single sample here. So as you can see here, we don't have the summation. That means you don't have to sum up, from 1 to L. You just need to calculate this once. Then you can update it. Calculate this once, you can update that. Okay, so this is called gradient descent. But the question comes, in that way, that is, how do we select which I, see the subscription here, which I should we choose here? Because from previously, we don't choose. We just, the I will be from 1 to L, which is sum up all the observations here. But here, we just choose one I. So basically, it's random choose. So we're going to randomly pick one observation and use that observation's residual to actually as a direction to do the gradient descent. Okay, so this is randomly picked. So it looks like this. For the traditional gradient descent, it's very smooth. So basically, you start, for example, you start from here and you go. So, okay, I'm going to explain this a little bit. So every single ring here is a loss, is the level of the loss. Maybe the loss here is 200. It's going to be lower. It's getting lower and lower when you go inside. When you're going inside, 200, 150, 100, so on and so forth. Okay, so at this point is where we started the gradient descent. So basically, the gradient descent, goes a little bit further until it reaches the low, like a global minimum right here. So this is the lowest minimum, lowest loss level. So this is where we try to stop at. But that's actually very smooth, as you can see. This is the traditional gradient descent. But for the stochastic gradient descent, because we don't actually sum up everything, right? So we basically just like pick it up random observations. So you're gonna jump forward and back just like really randomly, just like this. So you're gonna go start from here, then go here, go backwards, forwards, then go backward, forwards. But as the, when the number of the repetition, as as the number of the updates goes like to a large number, for example, for 1 million times or 10 million times, at the end, you can always go back to the local minimum. Okay, you can always go back to the local minimum. But it's just like the process is not that smooth as traditional kind of like stochastic gradient descent. It will just actually goes back and forward because it's randomly picked. There's no kind of like rules. So at the end, it will actually converge to the local minimum. But the whole process is actually a little bit of kind of, a lot of fluctuations right here. So there's, a drawback and there's like, kind of advantage here. So advantage for the traditional gradient descent is that it goes very smoothly, directly go to the local minimum, but it takes longer time. So this path takes a huge amount of time. But with stochastic gradient descent, although it's not like actually a smooth kind of like movement, but it takes less time for you to get to the local minimum over there. Okay, so that's stochastic gradient descent. Any question with respect to that part? All good. Okay, now let's go to online learning. Okay, so what is online learning? Okay, I think we got a question. Sure, yeah. We got a question here. Oh, feature normalization. Okay. For this one here, you don't need the feature normalization for the gradient descent because as you can see, like a scale is pretty much the same. So for this kind of like data set, you don't actually need that. But generally speaking, for the gradient descent, it doesn't make a difference if you normalize it or if you don't normalize it. It doesn't make a difference because for the linear regression, how do I explain this? For linear regression, it's not about scaling. No matter you scale it up or scale it down, as long as it's like the same kind of like a range, the beta is not going to change. For example, I want to write this. For example, it depends on the model, by the way. So for example, we are doing a linear regression. So normalization will increase the processing time. No, it's actually not right. It's not for linear regression. So for example, we're doing a linear regression that y equal to beta 0 plus beta 1 x. Okay, so if you do the normalization, for example, if I actually scale a little bit up, scale 2y and 2x. So now I multiply the y by 2 and multiply x by 2. Then I do the whole regression again. Beta 0 and beta 1 should not change. It actually doesn't change. So if beta 0 and beta 1 doesn't change, the whole kind of processing time shouldn't change as well. So basically, when you do the normalization, so I'm going to do this way, for example, let's go back to the map. When you do the normalization, it's just like this part. It's just like the vertical axis and horizontal axis changes. So as Brandon mentioned here, so when you do normalization, probably it doesn't start from -100 or 2000 here. It actually starts from -500 to 1500. I guess the calculator range of theorem will be a lot faster. Nope. So if the range of the data is actually greater, when you do the calculation with this part, when you do the gradient descent, when you do that part. So Brandon, you can talk. You don't have to type. You can actually talk. So it's not about multiple feature or not. It's about the residual here. So if you actually increase the y here, you increase the y, or you normalize the y, you normalize the x as well. So the residual here will be normalized. So the scale will actually change correspondingly. For example, previously your residual could be 200, but now if you increase y and x, it could be 2000. So now the gradient increases as well. And learning rate is now changing. So it's basically this part here that actually increase. Okay, so if that part increase, that means you're going to have a bigger jump. If that's a bigger jump, so with a large data set, it's going to have a bigger jump. If that's the case, then you're going to have the same time as a smaller data set with a small jump. So basically, it's the same. For this loss function, I don't know about other loss function, but for this one, normalization doesn't change. Normalization doesn't actually affect the whole kind of processing time. So basically, Brandon's question is, so for example, let's go back to the loss function here. If we normalize the y, normalize the x, will the processing time be reduced, or will the processing time will be increased? For example, previously, we have this regression here, and after previously we can have this regression here. After normalization, the y could be smaller than before, and the x could be smaller than before. Beta 0 and beta 1, in that case, it shouldn't change. That's the first point. Second, when you do the gradient descent, if you normalize it, the gradient descent will be smaller than before. It will be smaller than before. That means you make a smaller move than before. If that's the case, that means your update is actually getting a little bit slower compared with a large data set. So basically, the time shouldn't change. Basically, you are just like, increasing and decreasing at the same scale. So for the ordinary least square, for the linear regression, scaling or normalization doesn't actually change the gradient descent, like the decreasing time, or actually it's the time you go to, they span actually going to the local minimum over there. But for other kind of like a loss function, I'm not sure. For other loss function, it could be, for example, if you actually do the k-means clustering, it could be, because scaling is actually gonna affect the distance between different observations over there. But for this one, it shouldn't actually affect the whole kind of processing time. Any other question? So I guess, I don't know, to answer Brandon's question, to make it more clear, for example, let's take an example. For example, we have 100 meters. And you try to finish 100 meters with 5 steps. Then each step is going to take 2 meters, 20 meters here. Okay, 20 meters. So after normalization, probably you only have 15 meters. And now you can take, for example, you can still take 5 steps. And each step you're going to take, 10 meters. If that's the case you have, you actually normalize the 100 meter to 50 meters. The number of the steps you take is still the same. It's just like, how much you move, it actually shrinks the same scale. So you reduce the total loss by 50%, and you also reduce your step, like how big your step is by 50%. If that's the case, you are reducing both by the same amount of time, same amount of numbers, then the number of steps shouldn't change. So that's the core idea for the ordinary least square. Okay, but for other loss function, this is only for the ordinary least square, but for other loss function, it could be different. Okay. Okay, I'm going to keep going to the online learning part. So, so this actually follows like a stochastic gradient descent. So even with stochastic gradient descent, sometimes we have to, like for this one, we have to repeat like a lot of times, like 1 million times. Sometimes it's still gonna, use a lot of memories like on your computer. So what should we do? What actually should we do to avoid that kind of thing to happen? What should we do to actually reduce the memory occupation over there? So you can think about the case of paired regression. So like this kind of like regression we had before. So now what we do here is actually so previously when you do the gradient descent, you actually put the data, you store the data on your RAM, on your memories, on your like a local drive memories over there. Okay, so it's gonna take a huge time because you were actually passing the data set to your local RAM, and it's gonna pass back and tells you what's the next W is gonna be. So this kind of forward and back work actually takes a lot of time. So online learning basically just one thing. It doesn't use a local RAM. It doesn't use a RAM. It actually uses a hard disk drive. It actually uses HDD. So basically, you can store it on the temporary space. It stored it on a temporary space, just like a Spark. You stored it on a temporary space, which doesn't take any kind of local RAM over there. Then you're going to extract the data from there forward and back. Then after everything, you're going to erase it. So you don't actually store anything. So this is going to improve like the speed dramatically. So this kind of approach is actually called online learning. So if you want to know more, if you actually want to know more about it, so there's like this kind of like paper by Stephen Boyd, and he actually discussed a little bit more on this part. But that's online learning part. But in total, like, generally speaking, so for the online learning and the SGD, basically, especially for the SGD, we can use the SGD classifier, SGD regressor from the sklearn linear model, which I think, another lecture going to show you in the demo of the assignment later. So, and a WW here is going to tell you, like, the third part, WW here, the verbal rabbit here, is actually a typical case that uses online learning. Instead of using local, like a drive, it actually uses our HDD. So WW here are going to show you, like, another lecture going to show you how to use a WW that actually going to give you a faster training speed. Basically, for the same kind of logistic regression, I actually tried it myself. Previously, it could take like 5-4 minutes to get a result, but WW can just give it to you like in like 10-20 seconds. So it should be really quickly with this kind of library here. So that's my part. So I'll actually transform this to the next presenter and let her share her screen here.
Hey, sorry, there was some technical issue, so I guess we can resume the second part right now. And thanks, Daniel, for the part one. So I will take on talking about the label encoding, the one-hot encoding, and also hashing trick, all the fun stuff. So again, before the Zoom meeting, I've already sent out the Jupyter Notebook and also the data to the WeChat group and also the Zoom. So the Jupyter Notebook I'm going to walk through is called Categorical Features Processing. So first of all, there was a question I would like to ask anyone here. So why do we need to do encoding for categorical data? So I will probably give out 5 seconds if any of you would like to type your answer in the chat group, the chat box. Okay, doesn't seem there was like an answer, so I would just like to speak about that. I think Daniel kind of mentioned in part one already. So essentially, especially for categorical data, it's different than numerical data. So again, for categorical data, we're talking about any value that would not necessarily be like a number, or even it's like a number, it doesn't represent the typical numeric values that we understand. For example, yes or no, or January, February, December, etc. So those would be considered as like a categorical data. So as mentioned in the paragraph here, essentially we need to do encoding for categorical data because a lot of classification and also regression algorithms operate in Euclidean or matrix spaces. So which means the data is represented with vectors of real numbers. So simple answer is for a lot of classification and regression algorithm, you cannot just plug in the categorical data and then to hope it works, especially if your response is in categorical data such as logistic regression. So therefore, we need to process this kind of data. So essentially using encoding to convert it to more like a numeric values, and also at the same time does not lose the value itself, to make sure that we can use the categorical information in most of the classification and also regression models. So the data I would like to walk through with you today is called the UCI bank marketing dataset. So the link is here, and also for your convenience, I've already downloaded the full data, and as I mentioned, sent to the WeChat group and also the Zoom already. So again, the first box of the code here is the same code as what Daniel demo. So pretty much is to import a bunch of libraries from scikit-learns, pandas, convert it into abbreviation, and also to import the warnings function, but to ignore the warnings, pretty standard setting, and also to configure the inline background as retainer for visualization purposes. So first of all, I will import the data, so the bank full data into the pandas data set. So in this case, I also open up the CSV already. So the original CSV, as you can see, the separator is in semicolon. So therefore, I also define the separator here as semicolon, and delimiter will be none. So just to quickly look at how this data set looks like using the head function. So as you can tell, a bunch of columns just by glancing through, I think some of the columns would have categorical information such as job column, marital, education, etc. So the response or the label in this case will be the last column, Y. And the reason I'm doing this is I think the original code being provided by author pointed to the training data and also the label data set, which I was not able to find it on the link being provided. So pretty much I tweaked the script a little bit to generate my own data frame and also the label data frame. So also to quickly look at the data frame using the pandas describe function. So again, as you can tell, some of the columns would still be in the numeric format, which also means the others could be in categorical format. So the numeric columns we have are, for example, age, balance, day, etc. And just also to quickly look at the data types to make sure nothing is off. So furthermore, to process the data, as I mentioned, so I would like to generate two data sets in this case. The first one would be the data set itself without the label. So in this case, I just quickly drop the last column, the response column, called Y in this case. And second of all, I generated the labels data set. So in this case, I just obtained the column Y from the original data set. And again, for both data sets, the total record counts are equal, which is good. And again, as you can tell, the first data set will contain 16 columns, and the second label data set will only contain 1 column. So, and then I would like to look at one of the categorical column named education, just to look at the distribution and also what this column, like what categorical information will contain in this column. So in this case, I just do like a quick value count and also to plot it in the horizontal bar chart. So in this case, for education column, there were 4 values: unknown, primary, tertiary, and also secondary. So as you can tell, the secondary value would have the most record counts amongst all 4 values. And again, I haven't done like a value count for each of them, but just by looking at the bar chart here, it seems the values for each of the count for each value should sum up to the total value of 45,211. So should be good here. So furthermore, there was a default library in scikit-learn processing called label encoder. So it's like a quick function pretty much to convert the categorical values to using label encoding function. So just to explain label encoding quickly, what label encoding means is the system, in this case for education column. So scikit-learn will pretty much go through the values. So there were 4 of them, and then to randomly assign 0 to 3 to 4 values. So that in this case, to quickly convert the categorical values into the numeric form. And again, for the other columns, if you have more values, then scikit-learn will also do the label encoding automatically. So pretty much to get the total encodings and also to assign the codings to respective categorical values automatically. So in this case, again, I call the function label encoder back to the values. And after the encoding, I also reprint the result. So reprint the results into the horizontal bar chart. So in this case, as you can tell, the total record count should not change because again, we're just doing the encoding for the value itself. And as you can tell, the categorical values have been encoded. So unknown would become 3 and secondary would become 1, so on and so forth. So in this case, after the encoding, the label encoding, I would like to replace the encoded. I would like to replace the original value with the encoded value. So in this case, after the replacement, as you can tell on the education column, all the values have been converted to the numeric values. And also, furthermore, I would also like to convert all the categorical columns using label encoding. So in this case, there was a helper function to do so. So pretty much to look up all the categorical columns and also to apply the label encoder formula to all of them. So after the label encoding, this is the updated data set. So as you can tell, there should not be any categorical values. All of them would be in the numeric form. An interesting thing I want to highlight here, which I will also go through in more details here, is because of the way that label encoding works. So for example, even though under different columns, for example, marital and education, they all seems to use the same type of numbering system, for example, 1, 2. But however, 1, 2 under marital and 1, 2 under education will be different. And sometimes it might confuse people as well if they're trying to use the same value, but compare across multiple columns. And to me, I think the label encoding probably works best for binary value, so yes and no, or true or false, because regardless of what kind of column you are using the binary type of values, true or yes will always be 1 and false or no will always be 0. So for binary type of information, the label encoding will usually have a lot less, will cause a lot less confusion compared to any other columns that will have that they are not binary in nature. So furthermore, as you can tell in the paragraph here, as I mentioned, because even though we have converted, I would say the categorical values to numeric values already, it does not mean that you can do the calculation because again, it's just the encoding. It doesn't mean the information is numeric in nature. So something to remember. So in this case, the example that we have here is pretty much to take like the same column, but 2 different rows and to do a calculation. So for example, the first record, the job in the first record minus the job at the second record. So in this case, 9 minus 2 will equal to 7. But again, it's meaningless in this case because you cannot just do the calculation simply on categorical values. Okay. So furthermore, we want to test out whether or not the encoding makes sense because as I mentioned in the beginning, the whole reason that we want to do encoding here is so that we can fit everything into the regression model and then to run the modeling. So in this case, we pretty much created like a simple logistic regression formula, and we also want to calculate the respective measurements from that regression model. So by looking at the precision scoring, recall scoring, F1 scoring on the binary response, no, and also yes. And very interesting, as you can see, which I wanted to highlight, is the precision, recall, and also F1 scoring for the yes response is all 0. Very interesting, hey? While we have the support scoring is 1,310. So simply what that means is this encoding is just not working, because it means in this case, the model actually is failing to predict the yes response. So which means we just cannot use the label encoding in this case, simple answer. And something I wanted to highlight more from coding perspective is, so in the original code, I think when the author tries to call out the revel here, he only used label stop revel. So if I do it, I think it will return me an error message. So in order to fix it, you actually need to put values dot before revel function, and then to generate the result. So something I wanted to highlight with respect to some glitchy of the original code. So moving on to the second part, because as I mentioned, it doesn't seem label encoding is working in this case, as there was a lot of limitations to it, even though it's quite simple. So in order to resolve it, there was another encoding method I want to introduce here. Is called one-hot encoding. So essentially, for one-hot encoding, what that means, because we know that binary response seems works fine in most of the cases, so 1 and 0. So what that means is we will just keep using 1 and 0 to represent the categorical values. So what one-hot encoding means is instead of changing the categorical values to multiple numbers, such as from 0 to 10. Instead, it will actually look at the categorical values and then to convert it to a categorical names. So in this case, for example, if we have 10 categorical values, then we would then what one-hot encoding means is it will actually treat the 10 categorical values as 10 categorical features or 10 categorical names. So in this case, as you can see, it will become like a header in the pandas data frame in this case. So 1 and 0 in this case is very simple. So 1 would represent yes and 0 will represent no. So in this case, it means for 10 features, there was only 1 feature available. So it would be feature 6, because all the other features would represent will have 0 value. So right now we want to test out if the one-hot encoder still works for the previous data set. So in this case, I would call one-hot encoder again from scikit-learn. And then in this case, I would convert all the categorical columns using one-hot encoder. And as you can see, in this case, it will actually generate a lot more columns. So in this case, 44 columns in total, compared to previously, let me go back to the previous data set. As opposed to previously, I think in this case, we only have 16 columns. Because the way that one-hot encoding works is, as I mentioned before, for every single column, so in this case, age, job, marital, etc., it will look at, okay, in this case for age, how many categorical values I have, same as job. So what it would do is it would look at all the categorical values and then to flatten it into the features. So that's why in this case, by using the one-hot encoding, we'll have a lot more numbers of columns compared to using the label encoding. It's just the different way the system processes the encoding. So after we, okay, there was a question from Ling. Okay, go ahead, Ling. The column is 1 all the way. Which table are you talking about? Are you talking about this table or you're talking about the table above? This table. So what that means is, okay, let me reframe it. So what that means is, as you can tell, the first column here, right, 0 to 43. So 44 columns here will represent different features. So in this case, it would map to the different categorical values here under the categorical columns. And then 0 and 1, it would just means, okay, for this feature, if it's 1, it means the data point will have this feature. And 0 means for this feature, this data point would not have this feature. So it's like a simple yes and no. Does it make sense to you? Okay, sounds good. So if there was no more question, I will move on. And again, but column 2 has value 1 all the way, column 2. I can double check because again, I'm just doing the hat here. So if I try to get like a more rows in this case, as you can see for the tail, like for the last few rows for feature number 2 is actually could be 0. So again, it's not necessary. It all depends on the data set itself, whether or not you will hit that feature. Okay, sounds good. Okay, so furthermore, as I mentioned before, we wanted to simply test out to see whether or not the one-hot encoding is working for this data set in this case. So again, also plug into the same logistic regression model and to look at the scoring here. So for the precision, recall, and F1 score, as you can tell, respect to the yes response, all 3 scoring have been significantly improved compared to the first table, because the first table, as you can tell, is all 0. So at least for the second table here, based on the result, we can conclude that at least the one-hot encoding is working, and it's working a lot better compared to label encoding. So just to re-emphasize, I would not recommend using label encoding for this kind of data set, just because especially for the categorical data, it has multiple values. Again, if you're having a data set which is just easy yes and no, binary values only for your categorical columns, you may still be able to use the label encoding. Okay. So I will move on to the third part, which is hashing trick. So again, hashing trick is a little bit, I would say, more complicated here compared to the one-hot encoding. Because essentially for one-hot encoding, as you can tell, respect to mechanism here, the drawback could also be if you're having, I would say, numbers of categorical values. For example, if you have even like 1 million something, then what you can, and also at the same time, you have like a large data set. So what you can expect is pretty much your table would be a lot more bigger, and then it might be very difficult for you to understand, for example, which feature would represent which categorical value, just given the way that one-hot encoding works. So in this case, we would like to introduce another solution for encoding, which is called hashing trick. So essentially for hashing trick, how it works is, I would like to go to another diagram here, just to simplify what it means. So it's on Wikipedia. So if you look at this diagram here, so essentially what hashing means is, first of all, you would specify like a hashing space if you know, for example, if you know how many record counts or the approximate record counts that you would like to do the hashing. So you would define the hash space first. So in this case, 0 to 15, and then you would do the hashing. So what hashing means is the system would randomly map the keys. So keys in this case would be the value you want to hash to the hash value. So for example, in this case, John Smith, it will be hashed to 02. Lisa Smith, it will be hash 201, etc. And again, in this case, we will also note that for Sandra D, it actually got hashed to the same value. And it's very possible that because we only have very limited hash space being defined here, so which means we will have the less hash space compared to the numbers of values that we want to hash. So in this case, it would call hash collision, which I will introduce more details later, and also to talk about some of the solution. So coming back to the Jupyter notebook here, so so essentially, there was like a default function in Python to hash the value. So it's just called hash. So in this case, if I want to hash like some random values here, so for example, university.degree, high.school, and also illiterate, so representing the values under education, then I can just call this function hash and then to hash the values. So in this case, as you can tell, the system will just do the hashing and randomly map those values to the hash values. And again, as you can tell, the hash values here is actually a very long number, which doesn't make quite of sense here, because again, like definitely we do not want to deal with this length of numbers all the time unless we have to. So as I mentioned before, you can also specify your hash space in Python. So in this case, I will just put like a small number to start with. So 25 for the hash space. So if I rerun the function again, as you can see, the hash value will actually change and also to become like a much making sense, like more sensible numbers. So university degree will become 19, and the hash value for high.school will become 19. And also illiterate will become 13. So in this case, as you can see, we actually have a collision samples already because the hash values for university.degree and high.school is actually the same. And in order to test out whether or not it's the same hash value, in Python, there was a function called assert. So pretty much is to test out whether or not the values are the same. I believe you can also use assert function to test out some of the other statement. So to test it out, so pretty much I re-identify the hash space, because again, if I don't re-identify here, I would lose out the hash space. And I call this function. So I want to assert whether or not the hash value for university.degree, and then in this case, applying the hash space or applying 25 is the same as the hash value of high school, applying the same hash space. So if I run this function, as you can see, there was no error message, which means the hash value are actually the same between the two. So in order to test out the other statement, so I change from equal to not equal, Python will actually return me the error message, which means they are not different. So which is not good, because if we want to do the hashing exercise properly, we definitely want to make sure the values we're hashing here are not the same, unless they are the same values. So in order to fix it, one of the thing you can do is to increase your hashing space to make sure that it can meet your need. So in this case, for example, if I change it from 25 to 50, I should get a different hashing value for all three values, which is good in this case. Okay, so I would like to test out on the other categorical information using the hash function as well. So in this case, imagine that our data set contains a single, so not married student who received a call on Monday. So his feature vectors will be created similarly to the case of one hop encoding, but in the united space with mixed range for all features. So in this case, pretty much I would like to run the one hop encoding as well, but also just to compare the results using one hop encoding and also the hashing encoding. So in this case, again, I think in this case, it's still using the same hashing space. So that's why we have the same values here. So job equal to student will be the same as the hash value for marital equal to single, so both 13. And day of week equal to Monday will be hashed as 2. So if I compare to the results using the one-hot encoding, so as you can tell, so pretty much the one-hot encoding is taking all the categorical names and then change it to the headers here. So again, as I mentioned before, each feature will represent different values. And in this case, so day of week, the hash value is 2. So that's why if you look at 2 here, the value will be 1, which means it's yes for feature number 2. And then I think 13 is hidden here as the horizontal view. So I just transpose the table so that I can look at all the feature. So for 13 in this case, we will also be expected to see 1 here. So which means for feature 13, it will be yes. And in this case, because it's just a simply yes or no answer, so even though 13 appears 2 from one-hot encoding, it will not tell you there were 2 values. It would just tell you whether or not there was at least 1 data set that hit a feature. Okay. So in this case, I also wanted to run the assert. I wouldn't rerun it again just because I ran it already. So in this case, I'm pretty sure that the hash values for job equal to student and marital equal to single is the same, which is not good because again, we encounter another hashing collision issue already. And I just wanted to emphasize again, in this case, when you run the hashing, it's actually taking the categorical name and also categorical value and to do the hashing on the combination. So in this case, the categorical name would be job and categorical value would be student. So the hashing actually works on the combination. It's actually a good exercise because in this case, especially in some data set, it's very common that we might have the same value but applying to different columns. For example, we could have the same type of binary response, but actually applying to different columns. For example, employment, yes or no, household, yes or no. So in this case, it's actually very important and actually very critical for the hashing to work on the combination, but not just the categorical value itself, so that we will be able to know, okay, what exactly this value is about. Okay, so as mentioned here, it's important to distinguish the same values of different features. Okay, so in this case, again, I took out the hashing space in this box. So simply how it works is just using the default hashing function. So it should avoid the hashing collision issue in this case. So if I run this function just to test out whether or not housing equal to no would be different than lower equal to no. So if I run it, it would give me no error. So which means this statement is correct. Okay, there was another question from Emily. So if you have 13 equal to 1, does it mean both job equal to student and marital equal to single are both true in this case? So just to compare a little bit, essentially this table, so the one-hot encoding is pretty much to I would say visualize the hash value in this case. So because as you can tell by running this hashing exercise, the hash value for job equal to student and also marital equal to single are all 13. So that's why for the feature 13, we do have a yes response, which means for hashed value 13, there will be at least 1 data point. And again, depends on what kind of, I would say, hash function you are using, because again, I think let me just rerun the hash space, maybe easier. So if I define it to 100 and then to rerun it, in this case, we wouldn't encounter the hashing collision. So if I go to the table again, I believe again, it's too long to display. But anyways, you will be expected to see one under feature 88, and then one under feature 13, and then one under feature 2. So I think in order to ease up the understanding, I would not simply make a correlation between the hash values and also the categorical values itself. I know there was like a relationship there, but also it depends on what hashing you're doing. Because in the previous case, because we had the hashing collision where we will have two values but with the same hash value. So if you are just trying to use the hashing table to interpret that, again, the hashing table would just tell you, would indicate that there was at least one data set that could be job equal to student, or it could be marital equal to single. But I don't think in that case, you'll be able to have sufficient information to conclude there were actually two data sets. I'm not sure if it answered your question properly. So in this case, in order to, I would say, resolve the confusion, the best exercise for hashing is you always make sure that you only have one hashing value to one categorical name and also categorical value, because otherwise it would just misinterpret and also misrepresent your data.
Sorry to interrupt you. I think like Emily, like I think you probably can kind of confuse between the hash space and like the hash value you have. So based on, I think, you know, Lin's actually just making it very clear. So all the values here, 0, 1, 0, 1 here, is just in the hash space. And all the value on the top, like, you know, like job equal to student, marriage equal to single, that's just a value you actually attributed to that specific status. Okay, so for example here, if you have the day of the week, which is 2, then in the hash space, it's going to give you a value 1. That means, oh, I do have a hash value for this value here. So basically 1 just that I have a hash value. It doesn't mean anything. It just means, it only means the existence of that hash value. So you cannot just say 13 equal to 1. It's not that case. So if you actually have the hash, like a single equal to marital, it will automatically give the 13s like on the column over there, 13 of value 1. That means you already find a hash. If you have a 0 value here, that means you didn't find any hash for the specific status over there. So basically it's 2 different parts. Okay. Yeah, that's basically my comments here. Yeah, sorry.
Okay, thanks, Danielle. So respect to the hashing collision, if you're interested in more details and then wanted to understand, okay, how can I resolve the hashing collision like further, there was an article being referred in the Jupyter Notebook as well. So pretty much it would point to the article being published by the Booking Data Science team. And also I went through the article quickly and also trying to, I would say, copy some stuff over. So again, as I mentioned before, so pretty much a collision resolution strategy is necessary, but also at the same time, it may not be very easy to fix it because it will actually require your very good understanding of the data. For example, what's the essential hashing space that I will need to configure? Because as in the example I showed you before, definitely you don't want to have a super low hashing space, which would result into the hashing collision. But also at the same time, you probably don't want to just configure nothing, because configure nothing, which means you might just have this. Again, having this might work if you are dealing with a super complicated and also big data, but for like a straightforward, simpler data that has, for example, only like hundreds or thousands of features, this might not be something you want to see or use when you're doing the hashing trick. And just by going to the article quickly, I think they also introduced some of the other resolution, which I wouldn't go into too much details today. For example, they mentioned the other algorithm called the ostrich algorithm, so potentially to also resolve the hashing collision. Okay, there was few more questions. So first one from Chen. Is it fair to say hashing trick has the same logic of genetic algorithm? Yeah, I also have the same question as Daniel. I'm not sure, Chen, if you can explain a little bit more what genetic algorithm you're talking about. You can also speak if typing takes a lot of time. A sequence of DNA and you assign one position with one feature. Again, I'm not a professional in the, I would say, human biology side, but I would just point back to the diagram. Okay, never mind. So again, this is the diagram I want to point to. So again, my understanding for DNA sequences, you will have like a defined sequence, right? And also the limited, in this case, more like a hashing space, because you're talking about like a 23 pairs, as opposed to the hashing function here, the hashing space can actually be almost like unlimited. And again, in this case, it's the system that does like a random assignment, assigning the key to the hash value. So I don't think it's the same compared to genetic algorithm. Okay, I will pause a little bit if there was any further question. If not, then I will pass it to the next speaker to talk about part 3. And thanks everyone. Okay, doesn't seem any questions. Thank you, guys.
Thank you, Linz. Thank you so much for the lecture today. I think basically Lindsay actually covers everything, and it's pretty clear like everything here is quite important. So any questions so far for Lindsay? No? Okay. So the following part will be me and actually another kind of presenter. We together are going to tell you a little bit more about VW, wobble rarity, like the library here. But I want to actually point out a little bit on the, let me just share the screen here. I want to actually, point out some of the really important thing here. One of the most important things is that, like, when you use a label encoding, you better just use it for a binary case, which I totally agree. Like, for label encoding, you better just make sure the number of the values you have is very small. Like, you only have 1, 2, 3, 3 different values. If you have like, over 10 or 20,000 values, you don't want to use a label encoding, because it actually, when they do the label encoding, it actually just, it follows the alphabetic order. So it starts from B, give it 0, B, A, S, I, C, 6, 1. So if you look at the first count letter, it just goes through, goes through everything alphabetically, which is not a random. So it doesn't introduce any randomness, and also it doesn't mean anything. Like, if you just actually jump from 0 to 1, what does that mean? From 1 to 2, what does that mean? Increase by 1 unit, it doesn't, mean anything. So Linz, actually, I totally agree with Linz on that part. And second part is a hash space here. So what is hash space? So hash space basically tells you the limit, like the total, like the maximum number you can attribute to each kind of value. If hash space here is 25, that means all the values here cannot exceed 25. Okay, it must be smaller than 25. It's not a negative, it's positive, but it cannot be over 25. So just like Linz just said, I totally agree with her as well. The bigger value you have for the hash space, the less possibility you are going to have the collision. Because if you actually compress everything into a really small space, it's very possible that 2 values will be attributed like the same hash kind of keys over there. So yeah, basically that's that part. So I'll actually, I guess I will let the presenter to talk about the VW library here first, and I'll make some kind of component on top of that. So I will actually stop my. So
Hello, can people hear me?
sure, yeah, we can hear you.
So actually, even before I get to this topic, I have the same facial expression as Jackie Chan. I thought it will be easy. This is basically section 3. It's just 4 case studies to show that why the Vopa Webby is one of the most powerful learning libraries, because it's have the advantage of the online learning, as Daniel mentioned, and also the hash trick, as Linda just mentioned about. And I'm just going to share the link here. If anyone needs the same, I think I will just just post the link here, just in case you want to have the same screenshot. But basically, what it shows here is not Python code. It's actually in the shell. That's why you see the escalation mark here. You just say that, okay, I want to access to the shell. But if you have this code in Python, you don't need this escalation mark. And the library is just called VW, very simple, but don't be fooled, because when you type the help, you can see there are so many arguments that is beyond believing. And I will talk about 3 things, but first I want to talk about what does that mean by number of weight of bits. This is actually correlated to the hashing trick that Daniel and Linda just talked about. And also other things I will talk about, including the OAA, I can search this, and also Engram. Just 3 of the arguments. That's even that is complicated enough. So first, let me show you what does that mean by number of weight bits equals to 18. I make a note here. So this one just means the 2 to the power of 18. Basically, the 2 to the power 18 equals to 262.144, and that's how much hash space you have. So for example, and that means that any of the value of the word or the category you see, you won't see as a word, you will see as a number. The higher the power, so to the number of 18, we'll have 262K of space. But if you increase to 19, so you will just times this by 2, right? But the downside is the higher the power, the more RAM is required. So usually in common practice, depending on your RAM, you won't go beyond 30. So I just have an example, because all the case studies will be based on the text, which means basically language and words. And for example, the machine, when it says a value called what, so for example, people ask a question, what is your name? It won't see what as what, it will see, okay, it will assign a value of a hash. It will assign a hash value of this. And then if you do according to the divisor, 2 to the power 18, then the remainder is 177.44. So in other words, the hash key is what, and the hash or the hash key is 17744, and the hash value is what? Any questions so far? That's a really important concept, because as we become to write sentences, it will be just a bunch of these values together. And of course, if the longer the sentence or the articles, the more likely that it might have a collision. But like Lindsay was mentioning, it might not be a big deal. Okay. If no more, I will just go to the display the library here. Okay, so this is a lot of the parameters. And the first case study, excuse me, is so is how it reads data. You will read the data in the following format. You will say, what is your data label and importance or tag? But grant you, these one are non-mandatory elements. Even though you ignore, it won't do anything. And then the namespace is just the separate feature space. So you can separate them by the horizontal line here. So those are the must. And if you want to put data here or to check what the data looks like, you can just follow this, saying that this is the label and this is the importance. Importance means weight. By default, it's giving 1 to everything. And namespace number 1 is what the car is. And namespace number 2 is the organization. It's from the University of Maryland. So this is 18 for the weight. Okay. So the first.
Okay. Sorry. I just wanna pause here for a second about this this part of explanation here. So basically, you know, this echo part. So basically, think about the echo part as one row of the data frame we have before in the panels. So 1 here is a y, is the target variable. 1.0 means how much weight you actually, you know, give to this observation here. And subject what car is this? This is just one feature. This is one of the feature. Think about the first column. And organization, University of Maryland, 0.5 College Park. Think about this as a second feature. Okay. So basically, we just extract one row from the whole data set. So that's how we interpret, you know, this kind of like this line of the VW here. So it's totally different from pandas. Basically, you're just doing some kind of Linux and the command, just extracting the rows from the data set. Yes, go ahead, please.
So this is basically similar to the head function, right?
Yeah, basically similar to the head function, but we just extracted one of the row. We just extracted one row, not 5 or 6. We just extracted one of the row here. Yeah.
Okay, thank you. So the first case study is just called binary classification. What it means is they receive a text or question, and then they want to see what category it belongs to. And by binary, they just want to see whether it belongs to the recreation in the auto section or not. That's why it's binary. So it's just yes or no. So this is how they read the text. Okay, they will extract the first article, and then they will display by the print function. And you can see that somebody asked a question about what he see in the park with 2 doors and called bricklaying, whether this one will belong to a reg autos category or not.
Yes.
Oh, I'm sorry, can you hear me?
Yeah, we can hear you.
Oh, I just have a question. So I'm really beginner, but I'm kind of lost here. Can you briefly tell me what is the purpose of this set, the VM here? So from your example, what do you try to present it to us?
So basically, you have a bunch of reviews or you have a bunch of articles, right? Mm-hmm. And those bunch of articles have different target names. So if you go up a little bit, yeah, so here are target names, right? So each target name is just one topic. You can think about, you know, the reg motorcycles, that will be the motorcycle comment or motorcycle articles, like in the middle. Reg autos would be, you know, just like an automobile, like a car kind of like category. So basically here, we just try to predict whether we're gonna loop through all the articles, we try to predict whether this article is a car article that belong to that category or not. So that's what we're gonna do here.
So it's a bit, it sounds to me it's a bit similar to the data dictionary, like like the search function, for example, on Google. Those related predicted, like is the related topic or not, right?
Yeah, kind of. So we basically try to classify each articles and try to give them a label, whether you're in this category or not. So think about this, whether we are trying to predict your move. Are you going to go out today or you will not go out today? So basically it's kind of like a binary, like 2 outcome predictions here. And the standard is we try to predict is automobile kind of like a category or not.
Oh, so like you have the target name here, but in the sample here, where
so the target is
okay,
a label. It's going to tell you whether you are in this or not. And all the other stuff like the data, it's just the axis. So target is Y, all the other stuff are the X, the features used to predict.
Okay, I think I'm more clear about it now.
Yeah.
Okay, thank you very much. Yeah.
No problem.
Excellent.
Go ahead.
Okay. So here, that's how the format is going to predict, right? And just saying that, okay, if we follow to the rect auto category, assign is 0, any other category assign -1. I know it's a little bit confusing just because the target is more than just yes and no, and it's 20 category. So when it displays the text, it will just have some formatting requirement, including, okay, this one, find all -3 just means we throw away words shorter than 3 symbols. Maybe it doesn't give us information to study anyway. And then we skip many of the symbols as well. So all you see is just a very long string of text that actually from this email asks a question about what car is this, right?
Yeah, so basically this is like the same as before, but we try to transform it into VW format because it doesn't accept the pandas format. So we have to do the transformation. So as you can see here, we only have one X. We only have one predictor, which is the article here. And the label here is 1 because, just like in the beginning, because it belongs to this kind of like category. Yeah, go ahead, please.
So after it has all the train and other functions that I won't dive into, I will just say that, okay, this is what's important about this engine, the specification of this multi-rapid model. It just say that, okay, go to load this path and use a loss function of hinge. This is one of the, it's very important to follow exactly this syntax because that's the argument requirement. However, for loss functions, you don't have to choose hinge. You can choose other options. You can refer to the help to see how many options you have. And then basically, this will run the model and it will say that, okay, I will calculate this. And by the first article, I see that it doesn't belong to the auto vehicle category. And then, but because I'm still learning, so my prediction rate is actually 0. But as you can see, the loss function decreases as you have more trained samples. After you have all the trained, you can see that, okay, your example is becoming more and your prediction is becoming more and more accurate. So except for this one, belongs to the recreation autos, the other one belongs to other categories. And you can see that when you're in the 128 examples to read through those tags, the prediction rate is not really correct, but as you train more, and your loss function become less, the prediction is almost as accurate as the correct label. So this one just means, okay, I'm going to apply this model I just trained, and I'm going to apply for my test set, and to see whether what I predict and what is the actual data are the same. So you can see that in the training data, test data set, you don't know the label, but with the model you can predict, okay, this means yes and no. I'm still not sure why it has like a, I think it should be just 1 and -1, Daniel, but I don't know why.
It's a possibility over there. So basically, it's gonna tell you if it's 0.89, that's gonna tell you, 80% of the time, 89% of the time it's gonna be 1, and 20% of the time it's gonna be -1. That's a possibility over there.
Okay, cool, thank you. So this is just show the prediction of this model library, and you can see that it's almost 100% correct, right? With the AUC line, with both ends, the true positive and the false positive all attached to 1. Okay. Any questions so far? If not, I'm just going to move to this multicart classification. This is similar to the first example, except that now you have like more than 2 classes. So I will introduce this concept here, the argument called OAA. This means one against all, which means that you are going to include all the other classes. So the target news group, whatever the number of categories, it will just compare that each data set with the whole groups.
So I guess now, as you can see here, in the current prediction over there, so no matter it's the test data set, or if you go above a little bit to the training data set, it's not -1 or 1 and more, since it's multi-class. So basically everything is the same. We just transform to a multi-class. So now it's like predicted it's going to be 1, 2, 3, 4 until it's like 20 classes over there. So if you look at the second last column over there, current prediction, that's the final prediction we have.
And another thing I didn't mention is taking a very short period of time to do the whole calculation. It's milliseconds, right? Okay. This one is an interesting one. It's about to predict whether the movie review is positive or negative. So you just have a few case study, and then you separate the set by training and test with the same number. And then this one, just like one of the review, 0 days. That's a movie name. And then you will just say that, okay, from this, whether 1 means good review and -1, or 0 means bad review. And if you have like a blog and there are multiples, you want to rate whether how many good reviews versus bad reviews, this can be very helpful. You can just feed all the data into this model, and then you will be able to see whether the movie is well received or not, right? So the accuracy is pretty high just by reading those words and translate to a hash value, right? So one interesting argument he used here is called the Engram. So the Engram really means what is the next word according to the sentence is going to say. Either, let me see. I just have an article that I can share with people if they're interesting. And what does that mean by Engram? Basically, for me, Engram is just by the word I'm going to say, you are going to predict the next word I'm going to say. So for example, if I say the, and then what's the next word I'm going to say? You might have a lot of answers. But if I say, I'm going to tell you a movie name, and the movie starts with the 6, you might be saying that, okay, based on the first two words, the 6, I know the third word you're going to say is sense. So by doing this, it's actually increased accuracy rate a lot higher. Because
so I just want to add a little bit of comment on the Engram here. So if Engram equal to 2, basically just like you showed over there, 2 words. So but it's actually used the previous word to predict the next word. So that is like you, for example, if I have a sentence, I like the movie. So you're gonna use I to predict like. You're gonna use like to predict the. You're gonna use the to predict the movie. So that is you're gonna use the previous word predicting the next word. So this is gonna improve the speed very much, like a lot, because you only use 2 words, and also actually increase the accuracy because you don't actually use a bunch of irrelevant words. You just use the closest word to predict the next word. Yeah, please go ahead.
Yeah. So yeah, Daniel's right. If you assign Engram equals to 2, this value, it means just based on the previous word. But if you assign to 3, that means the previous 2 words. And this is the last study. Basically, it's a big data set with 10 gigabytes. And it has 10 categories here. You just want to, basically, think about it as a classification problem, just according to what you see in the word choice, whether it belongs to one of the programming language between JavaScript or all the way to Swift. So those are the most popular data scientist languages. And then you can use again, see this OAA, which means I'm going to use 1 against all. And in this case, there are 10 classes, 10 language equals to 10 classes. And you are going to use the training data from training model from here. And you're going to save the model to model 10 million VW. And this B, remember at the beginning of the lecture, the B stands for, sorry, I didn't mention this. B stands for number weight of bits. So instead of using 18, you increase all the way to 28. So you are going to have a lot of hash space. And it doesn't increase the time too much, but still give very accurate result. So in conclusion, it just says that the VW library is very fast, and you just can use it on the online learning, and also the hashing trick will make sure that it has the optimal and fastest speed. That's it for me.
Any question from this part?
So it gives me the sense that like this VM library is mainly for the like like the previous presenter trying to say, right? If the data set is mainly not numeric, then it's like character whatsoever, and you want to do prediction on it, and this module, this VM package will be really useful. Is that correct?
Not really. So VW is commonly used for natural language processing. So that is based on, you know, most of the time you don't actually have you don't actually can, you know, put all the words, actually transform all the words into a numbers. So in that way, if you have a label for each kind of label, you know, a bunch of words, you can just do this. So basically, we try to find the topic of each kind of article there. But you can also, you know, use like a numbers as like as the axis or the features to do the prediction. So basically, previously all the logistical regression or the linear regression with a number, you can still use it with a VW here. But we just showed an example with you know, with a natural language processing side. But you can use it for other kind of like applications for sure.
Oh, okay. So like, but is there any advantage of doing so to the like numeric data set?
For sure, because VW actually use online learning, so it uses a hard disk drive. It doesn't use a lot of local RAM. It only uses like a little, like a small percentage of local RAM, so it's gonna actually save a lot of space. It's not like a, you know, forward the data forward like and back, so it saves a lot of time on that part. So in that case, it actually, you know, trains the data really quickly, and also it transforms all the texts automatically using hash trick. So you don't have to encode all the words yourself. It will just, you know, you just throw the words into the VW. It will do the transformation for you. So that also saves a lot of like efforts from your side as well.
Oh, sweet. Okay.
Yeah.
Thank you.
Yeah. So basically, VW is actually most commonly used for NLP. And if you have, you know, try to, for example, I mean, I know TD, like the bank TD is actually using it for a lot of like call center kind of business. Basically, you know, they record your call every single time when you call their call center, and they actually classify your kind of call into different categories. Are you for the credit card or for the debit card? So basically, they use this for the classification to classify all these kind of like content of the conversations into different categories over there. Yeah.
Okay. Thank you very much.
No problem.
Thanks, Anna.
Any other questions? All good. Okay, then let's move to the next presenter. Thanks to Dings for presenting the VW here. Oh, by the way, back to Chen Qian's question. No, it's not a genetic algorithm if that's the definition. So genetic algorithm basically just like it's binary outcome 0, 1, 0, 1 here. So basically you just you know, if it's on the second position, it's gonna be Tuesday. Hash trick is not like that. Hash trick is give you actually random numbers. It doesn't have to be 0, 1. It can be any other numbers. So it's like a random attribution. It's not like, so in this way, it's not random. Basically, you just pick the position and you give the value here. So it's not that case. And also hash trick, sometimes it has like a bridge in the middle. It actually attribute each kind of data into a bucket. Then inside the bucket, you know, there's a lot of like index for each kind of word over there. Then it's gonna attribute the different value to the word. So it's much more complicated than that for sure. So for the genetic algorithm, I would say it's more like a binary encoding. It's not like, you know, it's like a 2-digit binary encoding. It's not like hash trick. Hash trick is totally different thing. Okay, now heading to Tianpei's like his demo on the stochastic gradient descent. Okay, over to you.
Hello, everyone. Can you guys hear me? Okay, so I'll just do a very quick demo on the implementation of SGD regressor and then do a comparison with linear regression. Can you guys see my screen? Okay, so first we will just import all the modules that we need to use for this demo, and then NumPy, pandas, and then mean squared error, and then train test split, and then standard scaler, and then SGD regressor. So first we will git clone the repository of the data that we have, and then we open it with pandas, and then we plot the data. So on the x-axis, it's the weight, and then the y-axis is the height, and then we use x and y to represent the weight and height data, and then we split the data sets into test data and then train data for both x and y. And then going back to Brandon and Daniel's discussion about whether to normalize this data, I actually looked online. I actually went to the stochastic gradient descent, and then in here it says that it's recommended to for SGD, it's recommended to standardize it before we use SGD, since it's sensitive for to feature scaling. I also tried. So here, I also tried to try SGD without the scaling, and then so we see here. If we don't do scaling, and then we can see that, yeah, so the mean square error is actually really huge. And then I don't know why this happened, but if we standardize the data before we do SGD, and then we can see that actually the mean square error is only at 2.699. And then, oh, sorry, one thing I forgot to mention is that with or without doing the standardizing, we have to reshape the data before we do SGD, because sometimes the data might have so one feature might have several columns, and then so we reshape them into just one column for the X data. And then we also can also see that for the coefficient, this is I'm not sure if it's the W0 or the W1 in Daniel's presentation. Just yeah, so one is the W0 and the other one is the W1. I'm sorry, where is it? Yeah, and then so if we do a comparison between stochastic gradient descent regression with linear regression, we can see that the mean squared error is about the same. So the previous one is 2.699, and the other one is 2.67, and the coefficients are pretty similar between them. And that's the end of my demo presentation. Maybe Daniel can discuss a little bit about why like why the mean square error has is so huge if we don't standardize the data?
So basically, I tried it myself. It's like the time doesn't change. So
Yeah,
if you do the scalar or non-scalar version, if you do the same kind of SGD regressor, the time is the same. So it doesn't take a longer time or less time than that. So that's one point. Second is like, I guess it's because it's randomly jumping. So you can like it's not like smoothly we actually slide down to the bottom of the mountain. We actually jumping forward and back. So if you actually don't scale it, that means you put it properly, you are gonna jump to like a huge jump, and then you jump a small jump. So it's like you don't have a lot of like rules to follow. So there's a lot of randomness over there. So at the end, it could actually increase the total like mean squared average. But if you scale it, that means you can compress everything to a really narrow range. In that way, even you make a big jump, it doesn't actually give you a lot of like deviation from the right track you were actually traveling along. So I guess that's the reason, but I'm not sure. Yeah.
Okay. So thanks everyone. Does anyone have any questions? Yeah, like all the information you can all find on sklearn. So the SGD regressor and also SGD for classification.
All right. Any question for this part here?
Yeah, actually,
No?
for
Yeah? Okay. Go ahead, please.
For the demo, like the solution itself, they actually used they actually define a class, but I wasn't very familiar with the class, so I just doing simple but defining functions, and that's it.
Yeah. Most of the time we don't actually use a class. Like it's very complicated. Better just use the library we already have in sklearn. We can just use that. Okay. Oh, I do want to point out one thing here. So for the SD regressor, just like Tianpei just showed us right here. So there are several key arguments. The first one is that you have to tell them what kind of loss function you want it to actually calculate. So Tianpei actually specify here is square loss. It could be other loss here, like the maximum likelihood or some other like loss functions, right? Second, like do you want a L1 or L2 regularization or not? So Tianpei here just said it's L2.
So by default, you don't have to L2.
Oh yeah, okay. So you only have two parameters. You only have like X and Y. So you better use L2, not L1. Yeah, and alpha is the learning rate, I guess. Is that right?
No, alpha is actually
or the L2's like L1, L2's like a regularization term.
Yeah, regularization term. Learning rate is the ETA here, but
okay.
It's by default it's set to 0.01.
Yeah. Okay. So yeah, I guess that's all the argument here, and the learning rate is actually the most important part. Oh, so we got a question. What is the penalty here? Yeah, like lasso or ridge regression, exactly. Because you're using linear regression. So basically you have to try to avoid the overfitting problem. So you want to actually add L1 or L2 on top of that if you have a lot of features over there.
Yeah.
Any other questions? All right. Okay. Let's wrap up for today. I'll see you guys next week. I guess that's everything for today. Thank you so much for everyone who actually volunteered for the lecture today. You guys really helped a lot. Thank you so much.